not a war on women.
No, it's not. But it was just shocking with the numbers that were posted of like women that are dying just from like simple things like being treated with like an antibiotic.
Yep.
You know.
Blows your mind.
I think they said there was like a 70% decrease in the population of women in the past like 5 years.
That seems extreme.
Yeah,
I have difficulty
which
with
is
it.
what I felt like.
Yeah. What was this?
I was watching a TV show and it was like about something, it was an episode from like the late 90s where it was when the Taliban first took over.
Yeah.
And so, or first like, America first realized it was taking over. And they posted like a link for like news updates, so I thought, I wonder if they still got anything, they still got, so I looked up and the big headline was like, the Brunei stuff. It was weird. I think
Somebody's misquoting the statistics, I'm pretty sure, but I mean, it doesn't make the situation any worse or any better.
Mm-hmm.
But I'm sure the numbers are probably not correct.
I hope they're not correct.
Well, if they were, and speaking, the population would cease to exist in future generations. So, okay, centroids and moments of inertia. So today we're doing a little review of something else you probably should have had during statics. That is a quick review of centroids and moments of inertia. Can anybody tell me what a centroid is?
So the center of the mass, the balance point kind of.
Okay, so if it is of uniform density, then yes, it would also be the center of mass. So the centroid is the geometrical center. Or the geometrical average position in X and Y of the body.
So it's the geometrical center, it's not the balance point,
It's the same thing. If it has uniform density, it is the same thing.
and without uniform density, the balance point and the center are different?
Right. If they have, imagine, if you will. Imagine, if you will. Sorry, you guys would know what that's about. Anybody know what that's? Imagine, if you will.
That's this.
Okay. The Twilight Zone from the 1950s.
Oh.
Okay, so yeah, I wasn't alive then either, and I know it, so I'm just saying.
I've seen some of them.
That's it. Anyway. Okay, so imagine, if you will, a board, right? Like on a seesaw. We know the geometrical center is the actual physical center, the dimensional center of the board. But if that board has one end made of lead and the other end made of wood, we know that that's not going to be the balance point. Right? So you have to shift the balance point. So the centroid is the geometrical center. It is not necessarily the balance point. It's only the balance point if everything's uniform, if it's made of a uniform material, if the density is uniform. Okay, anybody remember how we found that? We'll just do the x dimension first. X bar, which is the position of the centroid. Anybody remember how we did that? From statics? Give you a hint. It's a ratio of two integrals.
Over the area.
Over the what?
The integral area.
Right, the area integral of the body.
It's the volume on the top.
Nope. I mean, it has units of volume at the top, but it is not just the volume.
Moment of inertia?
X cubed times volume?
No,
Just X.
just XDA. If you were doing a mass, if it were an actual body, it would be the integral of x dm over the entire mass divided by the integral of dm over the entire mass, where m is the mass. So essentially, it is, if we're doing it for a real body, you know, to find the balance point, this is what we use. But how do we know that that's the balance point? What is it that sets that to be the balance point?
Isn't it where the center of gravity goes to?
Yeah, but I mean, what means that that's the center of gravity? I mean, it's being, so saying that that's where the center of gravity is saying the same thing as the balance point. What makes it the balance point? What happens if I put my thumb there? It balances.
The opposite of horizontal force.
Not the resultant force, it's an equilibrium. All right, so all forces are zero and all moments are zero. Right, the sum of the moments is equal to zero about the balance point. Right? If that were not the case, it would rotate because the net moment would cause it to rotate. So we want to find the point where the sum of the moments equals zero. Right? We're going to find that position. So we're going to take the sum of the moments, right? Mass times gravity, in fact, factoring G out of this. The weight, the force, times X, divided by the total weight, total forces, is equal to the center point. Right? So if I take this piece and move it over here, what I end up with, if you think about it, X bar times that bottom thing becomes the total weight is equal to the sum of all the moments. Right? That's the total weight. You see this? And that's the moments, x times dm. Right? Again, we're factoring the g out, the g is the g on top and bottom. So in other words, the sum of the moments is represented by the total force acting at that position. It's essentially the point where we can put all the forces, right? The couple where we can put all the forces and know that we've got everything represented right there. Are you with me or not with me? Okay. So hopefully that's all stuff we remember from last year or 2 years ago, depending on who you are. Okay. Similarly, we would have y bar, the centroid in the y direction. Well, I should give myself more room. The integral over the area of y dA over the integral over the area of dA. We're in everything we're going to be talking about here. We're not going to worry about this because we're going to assume uniform density. Steel beam, we assume that it's got uniform density. Okay? Now if you have a compound shape, like that one up there on the board, right? There's a bunch of different shapes together. For a compound shape, this is equal to the sum of all the individual pieces, x bar A, over the sum of all the areas. So each one of these pieces, right, is an integral itself. We have a bunch of individual pieces. So we take the integral of the left arm, the integral of the right arm, and the integral of the cross beam. Each of those will give me I1, I2, and I3. Then divide by the total area, and we have the centroid. That make sense? Okay. And then similarly for the y. What's going on out there?
Stuck in that little bit.
It sounds like it's
The
like.
door was just good, so.
Okay,
Let's get out.
stop now. All right. Okay, so we remember that stuff for the centroid. Okay? Just review. If you got some weird shape, as long as you can mathematically describe the shape, you can calculate the centroid. If it's not something that you can mathematically describe, then you can go to a reference. In the back of this book, I know it's in the back of the statics book, so you can definitely go back to your statics book. I'm trying to see if there's any table of centroids in here anywhere. Goodness gracious. Centroids.
Is it this door right here, or is it the one?
I have no idea. We'll find out if they fall through the ceiling. Yeah, they don't have a table in here, unfortunately. Oh well. Okay, so you'll have to use your statics book. Go back to your statics book as a reference if you want to look up centroids for common shapes. What is it for a rectangle? Centroid for a rectangle. What's that? The middle, right? The middle of a rectangle, right? What is it for triangle?
1.5 base times.
No, that's the area.
Oops.
What's the centroid?
It's center and 2/3 of
Okay. For any
Minus
triangle.
the
So
1/3 base times.
you just answered for this triangle.
Some be zero.
it. Yes.
What?
It's where the moment some be zero. That's
What about,
Shut up.
what if I had this triangle? Hmm.
Would it be 1/3, 1/3?
So it's 1/3 of the way in from that side, and it's 1/3 of the way in from that side. No, I'm not drawing that very well, am I?
Wait, from which side? From that smaller,
From the
that
fat side. 1/3 from the fat side or 2/3 from the skinny side.
Wait, what are you saying?
What?
Fat and skinny?
This is way too complicated.
Okay. Let's do it with the right triangle first.
Okay.
Okay. It's 1/3 of the way up from the fat side, that's the skinny side, it's a point.
Oh, okay.
And then it's 1/3 of the way in from this side, right? Okay, so remember that for triangles? Put it, you remember know the point for, well, let's not belabor the point. Let's move on, because I'll be here forever, okay? So, you can look them up, that's why. It becomes increasingly complex as the shapes get more complex. Okay, that's the centroid. But then we have the second thing called a moment of inertia, which is not really what it says it is. I don't understand why they call it moments of inertia, and that makes no sense to me why they call it a moment of inertia. It is the inertia of the moment, as opposed to the moment of the inertia. I don't understand. Right. It's the inertia when discussing moments. It's the inertial, it's the resistance of a body to a change in rotational motion. It is its inertia when dealing with moments. Right? Its inertia when dealing with forces is just its mass. Its inertia when it's dealing with moments is the moment of inertia, which should be the inertia of the moment. But that's all right. Moment of inertia.
I should keep saying that, but we won't know what you're talking about at all.
Yeah, exactly. All right. So inertia, right? We're trying to find the moment of inertia. Remember from UFIS or in dynamics. We'll talk about that next semester for anybody who's taking dynamics. In the y direction is the integral over the entire volume of the density times x squared of each volume element. And so a mass on the end of a weightless string has an inertia of mr squared. Remember that? Mr squared for the moment of inertia?
That's a volume integral?
That's a volume integral. So in other words, a mass, a ball, sitting on the end of a string, assuming we neglect the weight of the string, and try to spin it, right? Try to apply a moment, or a weightless stick. We try to spin the stick, right? I'm creating a moment about the stick, and I want to see how it responds. The inertia, the resistance to change of motion of that mass is its density times its volume, which is its mass, times x squared, x being the position in the x direction. Because I'm trying to find the moment about the y-axis. See what I'm saying? So in other words, if I look at the picture, right, here's the xy system, and here's my mass, I'm trying to spin it about the y-axis. So the dimension I care about is its x dimension. Right? And it's mr squared. But I want to go through each little bit of mass and integrate over the entire volume because they don't all have the same x. Right? Now for a sphere, a point mass, I take it to be a single x at the center of that sphere. But the reality is that x varies from point to point within an object. So that if I have some oddball shape out here, instead, I have to integrate the whole thing. But so the y-axis moment of inertia is this, right? Now, most of the time, if I have a two-dimensional representation of that object, right, if I'm doing working in a two-dimensional system, this is some kind of a plate, and its thickness is uniform. Right? If it were not, it would be a three-dimensional problem. So if I have a plate that's thickness is uniform, I can rewrite this as the integral of rho x squared thickness dA. Because I no longer have to integrate with respect to thickness because it's uniform. But density, we've already assumed, was the same throughout the body. And thickness, we've assumed, is the same throughout the body. So that moment of inertia is really the density times the thickness times the integral of A of x squared dA. So in the context of what we're talking about here, we're not going to worry about these constants. This is what we're going to call a moment of inertia. So earlier we had the moment of polar inertia. Remember that? J. Right, it was pi over 2 times c to the fourth for a round bar. Right. Here we have the moment of inertia in a well, really a two-dimensional sense. Okay? Similarly, Ix, the moment of inertia about the x-axis, is the integral over the area of y squared dA. And again, you got to keep in mind the x and y are different. Right, so if I want to rotate about the x-axis, it's the y position that matters. Okay. And then the moment of inertia about the origin, right? If I were trying to rotate this about the origin, so it's sort of some kind of a funky angle here. Well, that's going to be the integral over the area of r squared dA, where r is the position of the center of the centroid of the body. And that's no more than I sub x bar plus I sub y bar. Right? So hopefully again, it's all stuff we saw in statics. Yes? The origin you didn't see in statics.
Doesn't slope for
Okay.
So is the IX equals the isostat in the line above the J line supposed to be IX bar?
No, this is just Ix about the x-axis.
Oh.
See what I'm saying? That's just the moment of inertia about the x-axis.
I see what you're saying.
Okay. So, in other words, if this thing spun about an x-axis through its centroid,
Yeah.
as opposed to some other position x, so x, the y very depends on that. I'm specifically here talking about the origin, as opposed to rotating it about a point some out here, somewhere out there, some other point in space.
Yeah.
This is specific to the origin, that's why it's x bar and y bar.
That makes more sense.
Okay. Okay. How do we feel? Good. So maybe the J thing is the only thing that's new, everything else should be stuff you remember. Okay. And again, we're not really doing anything with this today. We're going to be using these moments of inertia as we go into the next section of material. That's why we're reviewing that stuff today. Okay. And then the final thing is for the moments of inertia. I'm assuming everybody remembers the parallel axis theorem. What's parallel axis theorem?
Something about something plus another something equals right something.
Something plus another something equals the right something.
It's like Ix plus Ix prime.
Okay. So the moment of inertia about some point about the x-axis. Let's see, let me draw a picture. Let's call this the centroid. So that this distance here is x prime, and this distance here is, I'm sorry, x bar and y bar. Those are the positions of the centroid. So the parallel axis theorem says that the moment of inertia about the
Would you say like one moment of inertia about one axis is the same as the other axis as long as the two axes are parallel?
yeah, not quite.
Isn't it flux? It's the same thing.
I
Flux.
should draw these in a different color. Let me redraw my picture.
Is it even close?
Well, let me define the thing, and then you can decide if you're close or not. So I'm going to create a different set of coordinate axes on here. So I have x prime and y prime, which are a different set of coordinate axes. Right? Okay? So what that says is that the moment of inertia about the x-axis is equal to the moment of inertia about x prime, that is the moment of inertia about the centroid. Let me write this about this. The moment of inertia about the centroid, which is the x prime axis on my drawing, plus the area of the object times the offset of that centroid to the original null axis, xy. Squared, sorry, squared. I forgot the square. Okay? And similarly, I is equal to I y prime, I'll write it as the y prime here now, plus a x bar squared. So y prime, again, is the offset of the centroid from the axis about which you're actually trying to rotate it. So I centroid or I y prime are the moments of inertia about the centroid of the object. That's why it's important to know centroid. You find the centroid, then from that centroid, you calculate the moment of inertia, where x in these integrals, right here, x in the integral is the deviation from the centroid. Right, so in the absolute space here, those x's are going to be x minus x prime, or x minus x bar. You follow what I'm saying? So, I can take that top expression and write it out. So the centroid piece is going to be y minus y bar squared dA Actually, no, it'd be y prime, right, sorry. What did I do? Yeah, that's right. Make sure my notation's right. Yes, okay. So, we're trying to find this Ix. So I about the x-axis. So it's going to be whatever my y position is, minus my y prime, or y bar position, is going to be the distance on the y-axis. And so in other words, this point here might be 2 above that. Right, so on the y prime axis, that's 2. The y prime position in there is 2. The y position of that is 2 minus the negative, I guess something like this, a plus value. Plus y bar. So if this is 8 and that's 2, then the position on the xy coordinate system is 10. The position on the prime coordinate system is 2. So I have the axis about the center, and I'm trying to find it about this other axis. So that equals, I just do the integral of a y prime squared, right, just doing the expansion there, plus 2 times the integral of y prime y bar. Actually, y bar is constant.
Wait, what are you saying, what is this equal to?
This is the Ix, sorry.
Okay.
So I'm just going back in here and saying, well, this is the result of the parallel axis theorem. And I'm sort of demonstrating the parallel axis theorem.
Okay.
Okay? Because we were having some trouble with the parallel axis theorem. If we'd known it right off the top of that, I would have just skipped this. Since we're like, it's something with respect to something plus something, we'll go through this. Okay. So the position on the y-axis is y prime position plus the centroid offset of y bar. Take those two, square them, I get this p squared, I get 2y bar times y prime dA plus integral a y bar squared dA.
You guys did DA in the first one?
Yeah. Just forgot it. Okay. Those are the three pieces. What is integral of y prime dA? This piece right here. That term. Integral over the area y prime dA. So, in other words, we're sitting here, right? This is where y prime is defined. If I integrate all of the y primes for the whole thing, right, y prime is defined with respect to this point, what am I going to find?
This area.
Not quite. What's y prime here? What did I say it was? What was y prime for that point right there? Nobody paid attention to me? Go ahead.
Like you said 2.
I said 2. All right, so that's 2. What's y prime down here?
2.
Negative 2. Right? 'Cause it's y prime. The y prime axis is centered at the centroid. So the integral of all the y primes dA around this thing,
Oh, is the difference in the area above and below something?
right? But what is the difference in the area above and below? By definition?
Oh, 0.
0. I'm at the centroid. There's just as much material above as there is below. I know I didn't draw it that way. Okay, but, right, because that's the definition of the centroid. So this center term here goes away because the centroid is the center of the body to begin with. So this whole thing goes to 0, and I'm left with then the integral of the area of y prime squared dA plus the integral of the area of y bar squared dA. What is the integral of y prime squared dA? No, this is y prime squared. You don't have cancellation. That is the moment of inertia of the about the centroid. Right, that's the definition of the moment of inertia about the centroid. Because y prime is defined as having an origin at the centroid. So this is the inertia about the centroid, and this is A times this constant. Right? The y bar can come out because y bar is a fixed constant, is the offset between the two coordinate systems squared. All right, so whether you like it or not, that's a demonstration, a proof of these relationships. Relax. Okay, so it's moment of inertia about the centroid plus A times the offset of the centroid squared. Okay? All right. All right, and then similarly, so normally the way this is written would be I x is equal to I bar x. Put the bar over the I, not over the x. Right, so in other words, it's a moment of inertia about the centroid plus A. What did I end up using? Oh, now, whatever the offset of the x is squared. And then similarly for the origin, you get the same idea. R d squared. Does that make sense? So essentially, I've offset this thing. I want to know the moment of inertia about something a distance d away from the centroid. So I offset from the centroid by a distance d. That d has an x component, which is the position of the centroid in that coordinate system. It has a y component, dy, which is the y centroid in that coordinate system. And as a result, I end up with this. And then the same for the y. I'm sorry. Gotta be careful about that. That's a y. No. Okay, so we've got centroids, which we have a good handle on. Moment of inertia, I think we've got a pretty decent handle on. And now parallel axis theorem says we just take the moment of inertia about the centroid, which is an important piece to know. So again, when you have tabulated values, typically what you have tabulated is the moment of inertia about the centroid. Because you can always add in AB squared to some other point off of the centroid. Okay, so when you the tabulated values are going to be the centroid values. So, if I look at this shape, and I say I want to find its centroid and its moment of inertia, right? I could come up with some complex integral that defines the entire shape. More likely, I'm going to break it into pieces and define the centroid and the moment of inertia of each of those pieces, and then combine them additively, because the centroids, right? We can combine the centroids this way, and the moments of inertia we can combine this way. Find the moment of inertia about the centroid of each piece, and then find out how far that moment of inertia is offset from the centroid of the whole thing. Yeah.
I'm not quite understanding how we're adding centroids together.
So
Are
you
we
add
summing them
each of
all
the
times area?
You take each centroid times the area of the object whose centroid you've calculated, add all of those up, and then divide by the total area.
Okay.
That's what this is. So if you look at this on the board, we can divide that up this way. I1 is the entire cross piece. It has a width of 4 and a height of 1/2. Where I2 is each of the two legs, and is one of the two legs, has a height of 1.5 and a width of 1/2. And I3 also has a height of 1.5 and a width of 1/2, so on the other side. Or, we could divide it this way. I2's now got a height of 2 and a width of 1/2. I3 has a height of 2 and a width of 1/2. And I1 just has a width of 3 and a height of 1/2. Right? And we could also do it this way, which is actually my preference. I1 is a whole rectangle that's 4 by 3, or 4 by 2. And then I2 is a smaller rectangle that is 3 by 1.5. And you simply subtract instead of add. Does that make sense? Did you guys do some of that stuff last in statics? Right, okay. So we can take either approach, and we'll come back and do this at the end if we have time. Okay. So the last thing I want to give you, which I'm fairly certain you probably did not cover in statics, and I'm not going to go through the full derivation of it because you can read the book, because it's a little more complex than what I've done so far. And that is what happens if we want to rotate our axes instead of translate them. So if we translate our axes, we have a solution for getting to the moment of inertia for an offset axis. But if we want to rotate the axes, which is typically something you want to do when you want to find the angle at which a max or min occurs. Okay, where does that have the maximum or minimum moment of inertia? So, let's see if anybody's got anything I want to use other than my book. I need to find my, all right, I'll use my phone. Okay, so, my phone has a moment of inertia about this axis. Right, so I can sit here and spin it. Right? That is the largest moment of inertia that my phone has. If I take all the bits and add them up, right, all the r squareds about the centroid here, I get the largest amount of r, big R squareds. If I flip it this way, we see that? Right? That axis, going through here, has the least r squareds. Right? All the things are really close to the center. So about this axis, I have the maximum moment of inertia, and about this axis, I have the minimum moment of inertia. I challenge you to flip a phone like this and get it to stay. Right? Get it to flip nice and uniformly in that direction, and it doesn't happen. See it? See how it tumbles? Right? Well, about this axis. It's unstable. It will not rotate about that axis, because that axis is somewhere between the maximum and the minimum axis of moment of inertia. What's that?
So you're gonna get broken phone bills.
No. I challenge you. I didn't say I paid for it. So you have a maximum moment of inertia and a minimum moment of inertia. And then there's that in-between thing. It's kind of funky, right? So there are going to be times when you want to find the maximum or the minimum moment of inertia for an odd shape, or some weird shape, right? That's not a right rectangular prism. So in that case, you're going to need to rotate the axes. So if we start out with an x and a y-axis, and again our funky shape up here, and we have some point, not necessarily the centroid, just some point, some element dA, and we're trying to find the moment of inertia of that element. And we have a y prime and an x prime coordinate system that have each been rotated by theta. Then this point is going to have an x prime value right? It's coordinate on the x prime system. And it's going to have a coordinate, similarly, on the original x coordinate system. And if you go through here and kind of do sines and cosines and all this kind of stuff, this is the part that I'm just waving my hand at. You can check in the back of the book, it's in an appendix. You'll find that the coordinate system for x prime, the coordinate x prime is equal to x cosine theta plus y sine theta. And similarly, y prime is going to be x sine theta. I'm sorry, y, never mind. It's going to be y cosine theta minus x sine theta. And that's all just derived geometrically. That's my y prime. So as I rotate a positive theta, you can see my y prime begins to get smaller. It's a subtraction. And my x prime begins to get larger. Okay, so you can kind of at least intuitively a little bit feel why this might be the case. So now if I take these two descriptions of x prime and y prime and plug them in for my moments of inertia over there, and plug them into the interval, actually solve the intervals, I find that the moment of inertia about the x prime axis is Ix plus Iy divided by 2 plus Ix minus Iy divided by 2 times the cosine of 2 theta. And then here's a new term we haven't talked about yet, Ixy times the sine of 2 theta. Iy prime, Ix plus Iy over 2 minus Ix minus Iy over 2 cosine 2 theta plus Ixy sine of 2 theta. So we end up with expressions for one in terms of the other. Expressions for the moments of inertia in the prime axis, the rotated coordinate system, in terms of the values in the original coordinate system plus the rotation angle theta. That's not particularly useful yet. Let me define Ixy. That's just the integral of xy dA as opposed to x squared or y squared. It's called the product of inertia. So that the product of inertia for the rotated coordinate system is Ix minus Iy over 2 sine 2 theta plus Ixy cosine 2 theta. Okay, again, it's just a bunch of equations written on the board. They work, but you know, it's kind of ugly. Here's the real value. We want to find that minimum or maximum axis. We want to find the axis about which the moment of inertia is minimized or maximized. So if we're going to do that, then we want to find the point where Ix prime or Iy prime, we want to find the theta value at which Ix prime or Iy prime is either min or max. Right? Some theta we can rotate this to so that Ix prime or Iy prime becomes a minimum or maximum. So we're essentially going to take dIx prime d theta and set it equal to 0. When you do that, you find that that angle, theta p, the principal angle, tangent of 2 theta p is equal to minus 2 ixy over ix minus iy. So you can find the angle through which you have to rotate it based on the moments of inertia and the product of inertia of the original coordinate system in order to get it to the point where you've reached either a minimum or a maximum. How much you have to rotate it. And at that point, one of these will be a minimum and the other will be a maximum. The minimum and maximum are 90 degrees apart, as you saw with my phone. The angle, minimum angle and the maximum angle are 90 degrees apart. And those values, I min and max, are equal to ix plus iy divided by 2 plus or minus the square root of ix minus iy over 2 squared plus ixy squared. All right, so that's kind of ugly. Just got a bunch of i's and x's and I just threw stuff up there. I realize that. But I want to make sure you understand that there is an axis about which we can maximize or minimize the moment of inertia. And that's going to have a lot to do with the strength when we try to bend these beams. Okay?
What was the GI y prime over?
And it doesn't matter whether it's IY or XY, it's actually the same thing, but I think I did that. I think that's, I think I said XY.
So what is that in relation to?
I'm setting the derivative of this with respect to theta to be 0, so that I find a maximum or minimum value of IXY, or IX bar, or IX prime.
Yeah.
In other words, I want to find whatever, I can rotate this around a whole bunch of different coordinate systems, right? I can take this blue axis and rotate it. I want to find the particular orientation of the blue axis that gives me either a maximum or minimum moment of inertia of this body.
So wait, does that mean it's the maximum, it's like the maximum axis or the maximum for that set axis that you define?
It is the axis at which the moment of inertia about that particular axis, about the prime axis, is the largest value that it could be, or the smallest value that it could be.
About the axis that you define?
About the prime axis, yes.
So then what was the principal angle?
That's that angle theta p from wherever I start. So I start out with ix, iy, and ixy.
Mm-hmm.
If I start out there, I can find out how much do I have to rotate it to get to this min and max orientation
Okay.
by just calculating the inertias for those.
I found that.
Okay. So we didn't get to do that, but I did give you, everybody got the homework problem? I'll probably stick this one in. Did everybody get the email I sent out about the homework problem for today?
When you just send it out.
Oh, yeah.
Last week?
Yeah.
Oh, that's.
It's just for you to practice on. It's something for you to practice on for going through your centroids and moments of inertia. So it's not, nothing I'm neglecting, but I could, somebody saw it.
Yeah, I think so.
So anyway, so check your email. I'll put this one on there too, and you can find out, maybe I won't, I don't know, I mean, I'm really tight for time this week. But at least I gave you a particular shape and had you figure out what the centroids were, the moments of inertia were, that kind of thing, so you could figure out, just get some practice doing this. That's all. All right. Really, Blake, you're taking off that fast, huh? I see, okay. I was going to congratulate you on what appeared to be a decent game.
Oh,
I mean,
yeah, I
we talked about Gwendolyn and
Yeah.
we're in good teams and all that, so. I'm going to follow up, but you know, you can don't down to the room, it's all right.
sorry, I got easy.
What did you
Yeah,
do?
it's fine.
Nothing, defense had a good game.
Yeah, it sounds like it. I can watch it.
Yeah, was it, did they stream it?
I don't know, because even when I know they're streaming it, I have a really tough time. Because
Yeah.
I'm usually watching on my phone instead of trying to watch on the computer, so it's a little harder. But anyway, yeah, kind of a drag. The offense didn't,
Yeah, story of our life.
kicking an extra touchdown or something, they'd been all right.
Yeah, I mean, we held them scoreless the last 3 quarters of the game, so.
Yeah, yeah.
And one of the scores they got was from our offense fumbling on their 11-yard line, so.
Yeah, right.
But I don't know, I mean, we're gonna watch film today and see.
All right.
But, yeah, I had a decent game, so that was at least
Makes
encouraging.
you feel good about it.
Yeah.
See ya.
Bittersweet.